Hi, I'm Alice. Once upon a time, I was a complex systems ecologist. These days, though, I'm a game dev. So, having spent a fair bit of time building both scientific simulations and games, there is a shocking amount of overlap. They both involve complex logic that has to be evaluated quickly, uncertain requirements and rapid iteration, all sorts of incidental bells and whistles, graphics, user input, audio, the ability to deploy to web. What a beautiful, brutal requirements list. Thankfully, we have tools that can help. They're called game engines. I happen to make Bevy, an open source Rust game engine. Honestly, I think it's one of the better options for some classes of scientific model. It's fast, flexible, and makes it really easy to manage complex logic and share reusable bits across your projects. But this talk isn't a sales pitch. Let's talk about all the cool ideas that you can and should steal from game dev, no matter how you're making models. So, when building models, I find it helpful to think about why am I even doing this? To me, there are three big reasons why you might create a model. First, to explore a system in order to build up a mental model of how something might work. Second, to communicate that model to someone else, whether they're a student or peer. And third, to use its predictions to make real world decisions. Every project will have a different balance between these goals, and how you both develop and design your model should change based on your goals and over the course of each project. When you are in that exploration phase, iteration speed is absolutely key. But to me, the most important lesson there is about the things you shouldn't do. There's there's two reasons why you should avoid things like optimization, polish, and architectural complexity. The most obvious one is that they're simply a waste of time. You're still exploring, and you don't need them yet. But there is a much more insidious reason. They actively slow down changes. That fancy numerical approach that you read about in a paper that gives you a 10x speed improvement, well, it's now much harder to see what some weird new behavior does because it doesn't fit into that mathematical framework. Beautifully formatting your rule book, it makes you changing your rules much harder and slower. Polish, in all of its forms, is a vital part of both scientific simulation and game development. But there's a time and place for it. Doing it early is not simply pointless, it's actively harmful to your project. At the same time, though, I see a lot of game devs and scientists making the opposite mistake. They're conflating rapid experimentation with rushing. The goal is to learn about the system you're exploring, and barreling blindly forward simply isn't effective. Instead, you need to think carefully about the questions you have and the answers you get, and think about how you can improve your certainty via the simplest, cheapest, most reliable experiments you can design. And then you reflect on those results to devise new questions and solidify your understanding and your vision of what your project should be. When the urge to polish and build something durable strikes you, there is something productive you can do. Improve your workflow and build up a solid foundation. For all of their differences, each simulation and each game share certain core foundations that can be reused across projects and persist even when you suddenly decide to pivot. The most important of these tools are the ones to make experimentation itself easier, letting you make changes faster and fix problems sooner. Game devs have all sorts of delightful tools and strategies for this that, as a scientist, you should actively steal. Make it easy to inspect the state of your simulation as it runs, and set up nice pause, play, stepping functionality so you can slow things down and examine what's going on. Spend some time investigating a solution to save the current state of the simulation and use it to define reusable scenarios and to create checkpoints for overnight model runs. Stop wasting time on compilation and explore tools like asset hot reloading or code hot patching that will really speed up your iteration times. And finally, take a bit of time to set up some automated tests and run them in CI. You don't need to go crazy, but testing tricky logic can save you a ton of time and heartache. Do stay tuned. At the end of this talk, I have a demo that shows off some of these tools. So, you've explored your system and you've drawn some interesting conclusions that you want to share with the world. Maybe that's some students, maybe that's your supervisor, maybe it's reviewer two at that fancy journal. How do you actually teach people with your simulation and persuade them that your interpretations of the dynamics of your system is correct and interesting? Well, I think you could take a page from game design here and teach people to learn through play. I know that's cliche, but I really do believe it. Games are incredibly complex things, yet even small children manage to figure out their nuances all by themselves. To do that, think about the key dynamics of the system that you're modeling and slowly and carefully unfold those dynamics with your audience. Start with the very simplest form and then slowly add mechanics, changing either the rules or the starting conditions. Write up the results of these little experiments, of course, but let the reader play and prove to themselves that this is what they're actually seeing and building up their own intuition for how the system works. As people get curious about the details, embed little explanations. Put them in places like tooltips and menus and little encyclopedias. Add cute the dynamic graphs, quickly summarize the state of the system for the user. Don't just dump all of this information on your poor reader up front. Organize it and let the curiosity draw them into the details. But how do you get people to actually engage with the simulation, to learn with it, to fall in love with it, and finally accept your paper to that high tier venue? I have one very weird, very important word for all the scientists in the audience to go look up after this talk is done. It's called juice. That's the term that game devs use to describe the way that games make simple, ordinary actions feel delightful. There's all sorts of tricks to learn here, but your two key goals are to focus on giving users feedback for every action they take and carefully highlighting the most important information. You might use things like color, sound, camera movement, animation, little puffs of particles. There's no add juice button hiding in your game engine. You need to figure out how to sell each action in a compelling and satisfying and ideally consistent way. Juice isn't just fluff and polish and smoke and mirrors, though. It serves a real practical purpose, even in scientific simulations. Simulations, just like games, have a huge amount of stuff going on. Proper juice makes it easier to use your software by focusing your attention on the things that matter and let everything else fade into a pleasant background hum. So, if and when your model makes it into production, you're going to want to make it go fast. Trust me. I know you want to make it go fast. Game devs have all manner of tricks here, but the single most important lesson that I've learned moving into game dev is that you have to measure. Speculation and vibes about why is my model slow? They simply don't work. No matter how smart you are, or what your grant says, or the idea that your supervisor has, you have to measure. There's there was only one way to improve the performance of complex systems. You figure out what's slow and you make that bit faster, and then you repeat that process endlessly. The best way to start approaching this is to profile your application. Use something like Tracy if you're using Rust, which uses spans to break apart your application into chunks and then automatically measure how long each of those spans take. Once you figured out what's slow, try and make it faster. If you're having trouble picking apart the signal from the noise, if you're doing these runs and you're saying, "Oh well, I did 10 runs of this, and maybe it's 5% faster, maybe it's not," it's consider making really pushing that part of your system to its extreme. Make little stress tests that spawn 100,000 tiles at once, or write little micro benchmarks to isolate that work and really amplify that signal. The last lesson that I have for you today is the hardest, most bitter one of all, as both a scientist and a game dev. Simply building something faster, more accurate, more fun than all of the competition isn't enough. If you build it, they won't come. You have to go out into the world and proudly share that thing you've made with other humans. I know, marketing. But the world is a busy place, and no one will ever care about your work as much as you do. It doesn't have to be fake. It's not all about ads and influencers and glamour journals. Think about why someone would care about the thing you've made and share that with them, clearly and proudly. Make it easy for them to find your work, easy to set up your model, easy to learn how it all works, and easy to contribute. And over time, you'll build a community of players, of students, of colleagues, of allies. Cherish and nurture that because it makes all the difference in the world. Thanks for being part of that for me today. So that's the first half of the talk done, and now it's demo time. So I spent some time over the last week mucking about, really indulging my instincts to please. I want to do science again, and building a little simulation. That simulation is open source. You can scan that QR code or check out my GitHub, and we're gonna show off the cool stuff that I've made, and ideally we can do this somewhat interactively, and you guys can ask questions, you guys can give feedback, you guys can make suggestions for things you want to see change, and I want to focus on the dev workflows that make iterating using a game engine so much faster than what I remember from back in my time in academia. So there's that. I'm gonna pull up my slides here and pull up the chat. Thank you. You've already posted the link. So as you watch, if you guys have questions, if you guys have comments, if you're like, oh, what happens if we do this, like, please do chime in, and we'll have a good time. So we have our this is a very simple Bevy project. It looks like Bevy, it looks like Rust, but we pull that open and we see a simulation. So there are three tools that I really recommend for iterating quickly with Bevy, especially if you're doing science. So the first one of those is just use a dev console. There's a really nice little Bevy console plugin that integrates with Clap, and you can say, oh yeah, please define this little command, and you define the little command, and then it just works, and it's so comfortable and so easy, and such a better use of your time than building out a GUI. It's fantastic. This simulation is in a state where it's designed entirely for exploration. It's designed for fucking around, finding out. It's designed for you're sitting there in your once a week meeting with your supervisor, and they're like, "Hey, what happens if I do this?" And rather than saying, "Well, I'll try that out and come back to you next week," it's, "Oh yeah, let's see what happens right now, live when they're over your shoulder," which is something that's incredibly powerful. So we're going to reset our simulation, reset, and hide our console with tilde. So this is a pretty basic ecological succession model with a little bit of fire. So we have, and we have these different states, and we're transitioning from lighter green to darker green, and then we have some fire going. And fire is more likely to spread in built up areas because there's more fuel. This is a simplified but not totally unrealistic version of ecological models that I was taught about and used during my time in ecology. And look, it's fun. It's a nice little. It's a lovely little cellular automaton. But okay, so the supervisor says that's very neat and all, but what if this was bigger? What if does that change the dynamics? Does that I want it to be bigger? And you say, oh, okay, sure, yeah. Let me pull up my inspector, entity inspector, which is the second tool. And okay, let's do 100 by 100. And you say, bam. And you can just change you can look at any of the resources you have, and you can go and you can change it. And you can say, oh, okay, let's look at our entity list. And we say, oh yeah, here's this tile. Here's its state. Here's the tile kind that this one is. This one is currently a shade tolerant forest, and it'll just automatically update dynamically. None of these tools, the console, the inspector, none of those things were built for the purpose of this. This is just taking our talks, taking the standard tools from the ecosystem and gluing them together. And that, to me, is incredibly powerful. It's incredibly valuable. So they say, okay, cool. That's neat. I like seeing that. Seeing that bigger. That's good. And what happens if we want to say, I think I like this, but I want to see the dynamics, a little bit faster. So instead of waiting a second between them, let's do 0.5. Cool. 0.5. No, that's not as fast as I want. We'll just let it go. We'll just let it blaze through. No, a little bit too fast. We'll do 0.3. Okay, so now we can see what's going on nicely. So suppose we wanted to say, okay, the supervisor says, what happens if we make it easier for fire to spread. So instead of a fire spread multiplier of 1,000, let's do 2,000. And then you can go and you can just live watch it. And you can see the equilibrium point changes. You get more light green, less dark green, more fire, just kind of stabilizing at equilibrium. And you're like, okay, cool. That's neat. There's all sorts of fun stuff we can do here. We can say things like, okay, let's change the fire susceptibility, the chance of fire starting as a whole. We'll increase that. Oh no, that's a lot of fire. Jeez, that is a lot of fire. Oh, back down to 0. Okay, and without fire, everything transitions to a stable, shady equilibrium. Okay, cool. So that's neat. But hold on. What's going on there? Let's just pause it. And then we can go in, we can zoom, we can go, and can say, oh, okay, let's look at this entity again. 55. You should be a fire. Yep. And that little pixel there, down there, changed. And that sort of flexibility, that sort of tooling, it makes all of the world when you're iterating, when you're exploring, when you're changing how these things work. And the fact that you can take an existing framework, you can take something flexible, and you can kind of beat it into the shape that you want without having to go and build this tooling yourself is incredibly powerful, because you don't have to waste your time thinking about how to design this, thinking about how to do it, thinking about how to integrate it with your project. It's so it's having tooling is very important, but it's also important to not let the maintenance of that tooling take over your main project. And it's that's something that I really like about Bevy, and I really like about the ECS, is that because everything uses such a consistent data model, it's very easy to make tooling that works for everything with a very minimal amount of boilerplate. So we got a lot of those. What else do we got? So we have something that's nice is we have a nice noise library. We're using classic Perlin noise here, and we can say what happens if we change the water threshold. You can see we get tiny lakes and we get islands, and the dynamics fundamentally change because these little forest patches are isolated from each other with the islands now. So we have the inspector, and we have the console, but there's something even cooler that I suspect most of you guys have not seen and are going to see a lot more of within the Rust ecosystem over the coming years, and that is hot reloading. So it's hot patching. So hot patching is something that has been kind of on the back burner for a few years now. People doing various questionably sound experiments, and that's the ability to change your code in Rust in real time and have it just automatically updated for you, and without restarting your application. And Dioxys, to their credit, has gone through and they've really refined this into a proper solution. So what we can do is we can say is within this is still fairly alpha, but we can say we can go in and we can edit these codes of any of these systems, and we can say, okay, that's going to change how this works immediately as soon as we hit reload. So let's do a really simple example. Spread fires. No, spread fires, you're currently going to do nothing. There we go. We're going to save. Oh, now all of a sudden my simulation isn't spreading fires. No, let's redo that. You save it, and hot patches, and suddenly we have the fire spreading. So you can see that exposing these parameters as resources is really useful for very, very quickly dynamically sliding it around and showing the values and all of that. But you don't need to even go that far if you want to implement complex logical changes, things that can't just be encoded in a number, things that can't just be exposed in a toggle. it's the ability to go in and hot patch things is incredibly useful for real-time development and for experimentation, and for your supervisor sitting over your shoulder and say, "Hey, I think I see a bug there. What happens if we do this?" It completely changes how you work, and it's I'm really excited about the future of Rust and the future of tools like Bevy in scientific computing for the future, because I would have absolutely killed for this. So we have a bit of time left. So does anybody have any suggestions for what people would like to see? Any sort of logic, any sort of experiments? Um, If not, we can try increasing the map size. Let's
So we
say
have
we
some
go.
people posting in the Q&A box as well as in the chat. I don't know if you found the Q&A box as well.
I have not found the Q&A box. Where's that?
So if you in the more menu, it might be hidden in there.
More in the more. Aha, Q&A. So these are good questions. So scientific projects often use the code only once, and you will not touch the code again, especially if we're not building a library. What's the benefit of using Rust over Python? So I would say that there is two benefits. So the first benefit is that a lot of the time, the libraries that it's you may not be reusing the code again, but you will be reusing libraries that are, and I tend to find that Rust libraries are more solid. They're a little bit more dependable than something that you might see in Python or R, or to a lesser extent Julia, um, because it makes it easier to maintain that. But the other thing here, and you'll end up, and part of that is especially around things like simulations where you want all of that extraneous functionality, and you're like, oh, okay, I want to go and have high performance graphical rendering of this is currently 1 million sprites, which is ridiculous. This is completely unoptimized. This is the stupidest, naivest way to do it, and it just works. You can just throw that out there because the underlying libraries are much more solid than something like Pygame. But the other thing is that I think that even if you are writing the code once and not using it again, you should try to reuse parts of that code across projects. Things like all like pretty much this entire project is just all scaffolding. The simulation itself is very simple, but you can take that code and you can copy paste it and use it as a template for your next project. Use it as a template for your next project, and eventually, like it's so much of the work is in setting up the scaffolding of things that are shared across projects that I think it's useful. Um, my other, I actually have a third point. I'm sorry, I'm a classic programmer fashion, off by one error, um, which is that something that really, really frustrated me as a scientist was trying to reproduce other people's results, even members of the same lab, and trying to go through and say, okay, there's this old simulation, there's this old piece of analysis. I want to go and run it. And it was, 10 years old or 5 years old, and it wasn't very well documented. And it worked on their machine, maybe, but it doesn't, sure as heck doesn't work on yours. And to me, that's one of the biggest strengths of Rust is its package management, its dependency management ecosystem, where it makes creating builds that can be reproduced and rerun 10, 15, 20 years from now not just possible, but the default obvious thing to do. And to me, that's really important in terms of things like scientific integrity, in terms of things like reproducibility, in terms of actually being able to build on the work of the people who've came before us. So we got another question from Shantanu. Is hot patching a feature of Rust or Bevy? A little column A, a little column B. So hot patching is very experimental, but Dioxys, via the subsecond work, has created a Rust, general solution for hot patching in Rust. There's been a little bit of work to glue it up to Bevy properly. But in theory, this is something that you could do for any Rust application, and I expect to see pretty much all of the GUI frameworks, all of the game engines adopting a solution there, um, which is exciting. Um, So, can I reverse time? Not in this current simulation. And that's definitely something that you could do. It's for a general solution. You would want to, for a general solution, you'd have to implement caching because there's no guarantee that your model is reversible. And in this case, it's not reversible. It that's it's an interesting feature, but that's the sort of thing where it's, oh man, if my supervisor was like, "Can you reverse time?" I'd be like, "Are you sure that's important? Are you sure we got to do that?" Um, so Laurentiu, Nicola, is that very simple sub-second second system. I assume it calls cargo itself based on the 1.3 second reload time. Indeed. Um, that is very simple sub-second system. We have a nice little ecosystem crate to help coordinate it. Let me close this out. I'll leave that open actually, and I'll show you my cargo.toml. So this is a ecosystem crate, and yes, it calls cargo kind of. I'm not entirely sure on the details of subsecond as it stands, but did you notice it interfering with Rust Analyzer rebuilding on save? Yes. If you are using Rust Analyzer, you should change your target directory for Rust Analyzer because otherwise it will block you from being able to call cargo run or cargo build. You need to separate those out, regardless of whether or not you're using hot patching, but especially if you're using hot patching. So this is the next question from Sam. Are there any issues between the time steps used for display versus simulation? If the simulation takes a long time to do a step, is that a problem? Do we need to worry about frame skipping? So the way that that's set up is pretty simple. So you're not gonna miss a frame. It will the way that this is set up is you say we're saying we have basically a timer, and we say if that timer has elapsed, then please run the next simulation. And so if the if the simulation step starts taking longer than a frame, then it will run every frame. We're not going to miss. We're not going to miss results. This is a pretty simple setup, but I think it's quite good. You just have have a run simulation system that runs the simulation schedule whenever you want it to, and then you just have a ready to run simulation step, which is just a timer and it's just a timer, which is fantastic. Does Bevy have GPU and or SIMD wrappers for easy use? That is a good question. So the answer is yes, it has GPU wrappers. It uses WGPU, and you can use compute shaders with that, which is quite powerful. I've seen entire physics engines implemented in WGPU to very good effect. Rapier has that, and it will require GPU programming skills, but it's entirely possible. In terms of SIMD, we don't have a ton of first class SIMD support. There was some early experiments to get that working as a first class feature, but it was very complex and hard to get proper testing and reviewers on. But it's our native math library. Glam is SIMD accelerated, and it's obviously possible to use other SIMD accelerated code for it. Done. All right, I think that's all the questions we have. Ooh, new questions. is your simulation being done on the CPU and then rendered on the GPU, or is it all done on the GPU? So this is 1 million. There's 1 million tiles, 1,000 by 1,000. And this is, here, let me make this as fast as I can. The added zoom is not helping my CPU. But so this is, it's not once per frame. It's not 60 FPS, but that's still, less than half a second per frame for a million. And the way that this actually works, I'll close this out, is dead simple. So this is all CPU based and just rendered on the GPU. And this is the simplest, stupidest, most experimental approach that you could do. So this is something that like a basic undergrad in their first approach would do. And the way it works is, for each of these tiles, we spawn an entity, and we just give them some components, and then we render them as sprites. We're not even using a tile map abstraction. We're not using anything. We're looking up their positions via hash map. We're looking up their neighbors via hash map. This is as slow, as stupid, as simple as you can get. And the reason for that is not because I don't know how to make it fast. It's not because I don't know how to optimize it. It's because I think that for as a base for scientists to experiment with, and as something in the experimental phase, it's prioritizing that flexibility of that entity-based representation is more important than squeezing out more performance, because I'm thinking about this as a scientist, as I have a little cellular automata. How many tiles do I really need to have before, in order to draw the scientific conclusions that I want from it? And the answer is, okay, yeah, maybe like 50 by 50. And for that, it doesn't matter how fast it is. It doesn't. It's as long as I can get 50 by 50 in real time, it does everything I possibly want in order to learn. And then as a result, we can do all sorts of things. Say you want it to go and say, okay, now let's add some planes flying over top and doing water bombing, like that aren't tied to the grid. Like, you could just do that. Like it's okay. Yeah, sure. If you have an optimized transition matrix model, and you're modeling these things via multiplying matrices together, absolutely that will be faster. But or you move it to the GPU, absolutely that'll be faster, but it will slow down your iteration time. It'll make it harder for you to answer those questions. It'll make it harder for you to add those nice features and that polish and all of those other goals. And so there's a real tension here. And so if for teaching, I've gone and in various spots I've left various notes marked with perf of, yeah, you can make this faster. But because I want to be able to iterate quickly, because I want to use this to teach other people how to make simulations, I haven't gone ahead and optimized that. And yeah, thanks, Philippe. It's I'm really happy to be able to showcase a little example of, like, okay, yeah, here are some very basic best practices for scientific computing in Bevy and for quick and dirty model simulation, because none of these things are very hard, but knowing where to start, knowing the tools and the tools and tricks and patterns to use is really valuable. So I'm really happy to have gotten this out there for the community.